This is a nice review paper that just came out that's worth summarizing here. It's focused on the ocean, past and future of ocean warming. I'm going to just read the abstract and then go through a bunch of figures. I'm reading the abstract because there are these numbers which are very important. Despite the uncertainties they come from, there are details that are important. Changes in ocean heat content provide a measure of ocean warming with impacts on the Earth system. We already know that. We talked about how ocean takes up more than 90% of the additional energy that's being trapped by anthropogenic increase in greenhouse gases. This review synthesizes estimates of the past and future OHC changes using observations and models. So all the observations are synthesized with all their uncertainties, bias corrections, quality control, and so on, and then they are compared to the IPCC class CWIP6 models for the past and the future to get a sense of where we are headed in terms of ocean warming. The top 2,000 meter of the global ocean has significantly warmed since the 1950s, so the heat has penetrated way down down to 2000 meters, gaining 351 plus or minus 59.8 zettajoules, where zetta is 10 to the 21 from 1958 to 2019. In case you don't appreciate how big this is, you can look at the number of the total amount of electricity produced on Earth every year, and these numbers are of the same order or higher. The rate of warming increased from less than 5 to around 10 zettajoules per year from the 1960s to 2010s. Observed area average warming is the largest in the Atlantic Ocean and Southern Oceans at 1.42 plus minus 0.09 and 1.40 plus minus 0.09 times 10 to the 9 joules per meter squared, respectively, for Atlantic and Southern Oceans. Obviously, this has a lot to do with the Atlantic meridional overturning circulation, deep water formation, and the fact that the Southern Ocean is a channel where wind forcing can take the surface heating and Ekman currents down to deeper depths, which then inundate in the Pacific and Indian Oceans as well. So this is respectively for the upper 2,000 meters for 1958 to 2019, the numbers for the Atlantic and the Southern Oceans. These observed patterns of heat gains are dominated by heat redistribution. So there are channels like the Indonesian through flow, the transports by the meridional overturning, etc., which accomplish this redistribution based on where it's being taken up and the residence time of that heat once it gets below the surface, away from the atmospheric exchanges. Observationally constrained projections suggest that historic ocean warming is irreversible this century. So the heat that's gone way below the surface, even if we manage to get to net zero and net negative even, the committed warming will continue, and the ocean committed warming is separate with its own very long time scales, and it's irreversible for a long time. Observationally constrained projections suggest that historic ocean warming is irreversible this century, with net warming dependent on the emission scenario. We'll look at that. By 2100, projected warming in the top 2000 meters is 2 to 6 times that observed so far, ranging from 1030 with a large uncertainty in zettajoules for low emission scenarios and 1874 zettajoules for high emission scenarios. As I've always said in many podcasts, 2100 numbers have to be taken with a pinch of salt because the scenario uncertainties begin to dominate everything at that point. The Pacific is projected to be the largest heat reservoir owing to its size, but the area average warming remains strongest in the Atlantic and Southern Oceans. Ocean warming has extensive impacts that pose risks to marine ecosystems and society. The projected changes necessitate a continuation and improvement of observations and models, along with better uncertainty estimations. Obviously, ocean warming has an impact on things like marine heat waves and the related impacts on the ecosystems, corals, fish, etc. Because the background mean being very high, natural variabilities like Atlantic multidecadal oscillation interdecadal Pacific Oscillation, El Nino, La Nina, NAO, they all begin to project onto the background warming, and the thresholds of marine heat waves will be met much more often. So again, we have to always worry about duration, intensity, and frequency of these marine heat waves and other impacts to see how climate change and ocean warming will load this dice of various ocean warming impacts. Principal processes and feedback loops linked to ocean warming. This is kind of the Earth system schematic, Earth's climate system with energy cycles. So ocean warming affects the albedo as well, temperature change, reflectivity. Ocean carbon cycle obviously has an impact. If with warming, ocean's ability to take up CO2 or keep the CO2 because of solubility reductions, then you can have a positive feedback with increasing carbon dioxide in the atmosphere. So far, ocean takes up about 25%. If this reduces, it will accelerate the warming, for example. And ocean transport and the redistribution, air-sea interactions, of course, sea ice interactions, freshwater input in terms of evaporation, precipitation, hydrologic cycle changes, which we put under water cycle, and of course there is the human system with ocean warming, committed change, interacting with the anthropogenic forcing. So even if we meet our climate goals to stop emitting more, and CO2 begins to decrease or flattens out, that cancellation of continued committed warming versus decreasing CO2 will affect ocean warming, with ocean storing its heat and having its own time scale of committed change in the ocean. The linkages of ocean warming to changes in the Earth system, of course, it affects the hydrologic cycle and hence the rainfall, will affect coastal flooding, coastal erosion with sea level rise, saltwater intrusions into the groundwater systems, coastal infrastructures, tropical cyclones which get most of their energy from the ocean. CO2 concentration increases if the ocean begins to become less of a sink, evaporation providing the energy, and so the energy imbalance at the top of the atmosphere. Sea ice, ice sheets, cryospheres, marine heat waves, ocean acidification, oxygen deoxygenation, also solubility reductions because of warming, salinity changes because of hydrologic changes, density changes, stratification changes which will affect biological productivity. Ocean currents will change, fisheries, aquaculture, ocean ecosystems and biodiversity, and so on. Obviously it's the whole kitchen sink, but each one has processes related to how the ocean heat uptake happens and how fast it happens, how it gets redistributed, and how it's affected by natural modes of variability and so on. So surface and subsurface ocean warming, it's worth reading this, even though it'll get a bit, the podcast will get a bit longer. The land atmosphere and upper ocean surface and mixed layer respond relatively quickly, as we know, to surface radiative forcing, whereas the deep ocean typically adjusts over centuries to millennia. That's the residence time of the water that gets down. Surface warming is approximately determined by cumulative emissions up to a given point in time, owing to a near cancellation between positive climate commitment and negative carbon cycle commitment. So accumulated CO2 is going to keep warming the climate in the climate commitment, whereas we are beginning to plan to reduce CO2 emissions, which obviously hopefully will come true, and then we'll have negative carbon cycle commitments. This relationship implies that zero CO2 emissions, assuming constant non-CO2 emissions, so converting to CO2 equivalent is one way to deal with that, lead to near constant global surface temperature. This is from Miles Allen's part of the 1.5 degree C report, which I'll show a figure in a minute. This is a finding that has critical implications for climate change mitigation. However, the subsurface ocean responds far more slowly to anthropogenic forcing, in part owing to the slow nature of large-scale ocean circulation. Future subsurface ocean warming therefore has a much longer commitment time. Once the heat is down there, it's not easy to bring it back up and equilibrate the system till the ocean is overturned at those time scales. Even after net zero emissions are reached, the ocean subsurface will continue to warm as heat is transported downwards into deeper ocean waters, and a positive Earth energy imbalance remains until ocean and land carbon uptake sufficiently reduces atmospheric CO2 concentration. So as we know, CO2 residence times are multiple centuries, and the carbon cycle equilibration takes a long time. Ocean heat content and sea level rise both integrate ocean temperature changes below the surface, the volume change, and they continue to increase long after surface temperature stabilizes. So sea surface temperature equilibrates with atmosphere on a much faster time scale, but the heat content below the surface will continue to do its thing for much longer time. This fundamental distinction between surface warming and ocean heat content increases has important implications for both mitigation and adaptation strategies, of course. Furthermore, as the measurements of sea surface temperatures rely on different instruments, the observations of SSTs are fundamentally different in their temporal and spatial coverage and temporal extent compared to subsurface observations and ocean heat content estimates. So a lot of reconstructions of sea surface temperatures for longer than a century have happened with various assumptions of filling spatial gaps and temporal gaps, but it's even more challenging to do this for subsurface heat content. Just as a definition, ocean heat content, of course, is the integration of Cp triple integral over xyz with density, temperature, and volume following these standards that are set, where Cp is, of course, the heat capacity of the water at constant pressure, rho is the potential density in kilogram per meter cube, and T is conservative temperature measured in degrees Celsius. Potential density is, of course, adjusted for pressure to a reference pressure, and conservative temperature is also similarly made to take care of the pressure changes, compressibility effects, and so on. So the Miles-Allen paper basically gives a nice schematic of how things work. This is the historic change that has happened, so estimated anthropogenic warming to date, and multiple products give you uncertainties because of the reconstruction involved, as we said. And then if you look at future scenarios starting in 2017, when the report came out in 2018, I think, observed monthly global mean surface temperatures, you can see that the likely range of model responses to stylized pathways are shown here in various colors. Global CO2 emissions reach net zero in 2055, while net non-CO2 radiative forcing is reduced after 2030 in gray in B, C, and D. So faster CO2 reductions in blue here, this range obviously will result in higher probability of limiting warming to 1.5 degrees C, which was the goal of this report, special report from the UNFCCC. And no reductions of net CO2 radiative forcing, shown in purple, results in lower probability of limiting warming to 1.5 degrees C. But essentially, it just says that depending on the scenarios, stylized net global CO2 emission pathways, you can push the decarbonization to an earlier date to get lower cumulative CO2 emissions, which obviously will also come with non-CO2 radiative forcing pathways if we don't reduce it after 2030 versus if we start to reduce them after 2030 and so on. So just keep in mind that it's the cumulative net CO2 emissions that determine the warming, and hence the committed warming, that even if we go to net zero, we are going to continue the net warming, while the carbon commitment will reduce that part of the ocean heating and ocean feedbacks. So just to quickly touch on natural variabilities which interact with the ocean heat uptake and ocean heat content, there is the Atlantic multi-decadal oscillation, which has multi-decadal timescales. It's averaged over the northern Atlantic box, basically from the tropics to high latitudes, and it stays positive in some decades and then goes negative, positive, negative. Now we are in a positive phase for a while, which means this adds to the rate of warming in the atmosphere. Basically, you are changing the relative amount of heat stored in the ocean versus giving it to the atmosphere, and so on. So you can see that the observed AMO SST pattern looks this way, warming all the way from the equator to the higher latitudes with some spatial loadings which are different. Whereas the North Atlantic oscillation is the oscillation between the Icelandic low and the Azores high, and has this pattern which is often referred to as a tripole pattern, warm, cold, warm. This of course changes the storm patterns and the climate over Europe and so on. So you can see that those are not exactly the same. And of course there is also the interdecadal Pacific oscillation, or the Pacific decadal oscillation, which also are affected by things like aerosol forcing and greenhouse gas forcing. I won't go into the details, but essentially we have to always remember that there are natural modes of variability like El Nino, La Nina, NAO, AMO, PDO, etc., IPO. They themselves affect global warming rates because of the change in heat storage in the ocean. Memory always comes from the ocean for low frequencies, but also they themselves will be affected by global warming. So this is a tricky business in terms of the feeding. Coming back to the results on ocean heat content, these are the estimated ocean warmings from 0 to 700. Obviously the uncertainty goes up as you go to the past because of the data coverage issues and so on. But from the satellite period, the results get much more confident from different reconstructions. That's good to remember. So the ocean heat content is not only increasing, but it's accelerating. And the rate of ocean warming in watts per meter squared, this is zetajoules in ocean warming heat content increase, basically for 2005 to 2019 baseline, which is 0. So we were below that and we have crossed over here in around 2010 or so. Ocean warming, again, multiple reconstructions, and you can see that unfortunately the CMIP 5 models have a range. So CMIP 6 for various scenarios, SSP 5 8.5, which is the business as usual scenario, which will take us into La La Land in terms of the rate of increase of zetajoules per year versus rate of warming in watts per meter squared. And the more modest SSP 2 4.5 will keep us here by 2100, and CMIP 6 2.6, which is the more benign one, to stay below 2 degrees C warming by 2100 with a 67% probability will bring us down here. But one has to keep in mind that future uncertainties are large, but even the past uncertainties in models are large because of various issues of mixing, overturning circulation differences, heat uptake differences, ocean redistribution differences in the models compared to observations. This is estimated ocean warming down to 2000 meters, again 0 to 2000 meters. Similar story, that we have begun to accelerate with the uncertainties between different estimates collapsing to a more robust result since the satellite data became available in the 90s. Early 90s. Rate of ocean warming, again comparing CMIP 6, uncertainties are high compared to observational estimates down to 2000 meter, but again the story of different scenarios is similar to the upper ocean heating as well, except that the committed warming, ocean heating committed warming, will be much longer if the heat storage goes this far in deeper depths, because again, losing it back to the atmosphere and equilibrating will take a long time. So estimated ocean warming below 2000, you can see various estimates a little bit all over the place, but more recently there is more confidence, and the uncertainties unfortunately still remain high, but this is why models need to improve and data need to improve as well. And the rate of ocean warming below 2000, again, large uncertainties, but adaptation mitigation plans have to somehow plan to account for these things. I won't go through the table, but basically if you look at the various estimates from various groups and observations and IPCC reports, you will see the numbers are a little bit all over the place, and the total ocean depth integrated heat content changes are also quite different, and even though the numbers may not look like they are large in terms of the differences, considering the amount of heat in zettajoules, that those are massive numbers, which just underscores the need to continue to improve the observations, at least from now into the future. Of course, there are regional patterns that are very important. These are ocean heat content trends for 1958 to 2019, so the historic period in watts per meter squared. There are clear ocean heat uptake places where the ocean heat content increases, and redistributions are involved in each situation, with Southern Ocean and the Atlantic dominating the heat content increases. But Pacific is a much larger area and integrated. It will dominate in the future. Indian Ocean, for example, gets excess heat from the Pacific through the Indonesian through flow, and some heat that penetrates deeper here in the Southern Ocean coming into the Indian Ocean with its meridional circulation and so on. And there are details of how the Mediterranean pattern is related to its exchanges with the Atlantic and its internal circulation patterns, and how that's affecting the bottom water formation within the Mediterranean, in the Adriatic Sea, and so on. So there are other details looking at future projections from the historical period, and how the heat will penetrate into the ocean for the baseline and the various scenarios like SSP1 2.6, which is the most benign one, and SSP5 8.5, which is the most destructive one in terms of business as usual, where we don't do much. So you can just see how zooming in gives us a picture of ocean heat uptake, how observations and various scenarios for the future merge together. Okay, so historical period is shown here as observation, and the continuous increase into the future is shown for SSP1 2.6. Similar figures exist for different regions. So this is global. So this is the global pattern. This is a global averaged, and these are for the Pacific, Atlantic, and Indian Oceans. And as we said, Atlantic Ocean and the Southern Ocean dominate, and you can see that here in terms of the impacts of the significant differences in the future over the Atlantic and the Southern. So Southern Ocean is here typically because it's a channel. It penetrates much deeper compared to these oceans. Of course, here there is deep water formation, North Atlantic deep water formation as well. Okay, that's the Mediterranean, and that's the Arctic. Arctic is getting Atlanticized, which means more and more of the Atlantic influences are coming into the Arctic, which is bad news, of course, with the polar amplification that is expected to continue even in terms of the ocean heat content increase into the future, and surface warming, and so on. Okay. Comparing to models, just as a caveat, one should always be careful, because this is for models which have low transient climate response, and there are some models which have high transient climate response. So as CO2 increases 1% per year for 70 years to double the concentration, you can see how models affect model specificities of their transient climate response, which is a integrated ocean, atmosphere, land, carbon cycle kind of impact. You can see that there are substantial differences in how deep the ocean heat uptake works, and this is the difference between low TCR and high TCR models. And you can see that these numbers are not small in terms of the heat content changes, and there are patterns associated with the North Atlantic deep water formation sites and the Southern Ocean mode waters and deep water formation sites, and so on. So this is ocean warming, and this is ocean heat content. So models have biases which lead to some problems, so that especially has to be considered when you look at the future projections as well. So this is total ocean heat content for the historic period. Again, Atlantic and the Southern Ocean dominate. If you look at 2050, that pattern continues, but the large Pacific Ocean is a significant storage of ocean heat content as well. And by 2100, The pattern of Atlantic and Southern Ocean dominance continues, but Pacific storage increases as well. But one must keep in mind that it depends on various scenario uncertainties and model uncertainties. So in the earlier decades, model uncertainties dominate. In the later decades, scenario uncertainties dominate. So all those things have to be kept in mind, but nonetheless, these are very important results that we must keep in mind. Okay.